Hi, so in the next few videos, we're going to talk about how to implement AVL tree, which is the assignment for this week. So the first one is about doing a little bit of preparation work. So the AVL tree implementation is, in my opinion, is neither too easy nor too hard, but it will definitely help you to understand AVL tree a lot better and make you a better programmer after you're done. So I will help you get started with the implementation. Having said that, excuse me, if you want a challenge, you're welcome to go with your own implementation. You probably still want to finish at least the preparation video, which is the one you're watching right now, but do feel free to skip the rest if you want to do it, go on your own way. Just if you do that, just make sure you do follow the assignment and the specifications. Right, so as far as the implementation goes, one thing to remember from doing the binary search tree and the lazy delete binary search tree is that if you try to think about the entire tree, it almost seems impossible. Where do we start? But if we focus on a single node, what happens on a single node, and just let the recursion to take care of the rest of the tree, then things becomes a lot more manageable. So for the AVL tree implementation, keep this in mind as we go forward. And now AVL tree is a binary search tree, right? So and since we already have an implementation for binary search tree, it's really kind of natural to have our AVL tree class to inherit from binary search tree. And just because a lot of the behaviors are exactly the same, right? We're not changing how, for example, find works, not changing how iteration works. So with some foresight, because last week I knew we were going to do the AVL tree implementation. So I actually make some modifications after we will talk about a binary search tree to make our implementation of AVL tree a little easier. So I'll explain those changes first. So the first thing I changed in binary search tree is that if you remember what's in the binary search tree, the only place where a tree node is created, is instantiated, is just in insert. That's when we wrap the data in an actual node and attach it as leaf node, right? I actually make that into a class attribute now. So we are not hard coding binary tree node in insert. That's a class attribute. And the advantage of that is it can be overridden by the subclasses, classes that inherit from binary search tree. So we know for binary search tree, the node should be binary tree node. But for our AVL tree, we'll actually create our own AVL tree node, but we'll override this attribute so that we don't have to override insert to create different type of node. So that is the first change that I made. And then actually we'll use the same idea for testing. So let me show you that BST test. So for testing, in BST test cases, we want to create binary search tree, right? However, we will actually inherit the test cases as well. And when the AVL tree test case, we want to create an AVL tree rather than a binary search tree to be used in the tests. So I also make that the tree type a class variable. So the subclasses can override that. We'll see how it's used in just a moment. And then lastly, one more thing that I did change is I added a repre. Then the repre method, this is, if you remember, includes more information about debugging. So it's helpful for us programmer to see what's in the tree. And so in this in this method, it will call the underscore string, which is a recursive function that kind of construct a tree, construct a string that's composed of uh, the string representation of each of the nodes, if you remember. And so basically, if this underscore repeat is false, it just works the same as before. We'll just convert each of the node into a string. However, if this is true, then we'll actually call the reprieve, then the reprieve function of the node to give us more information about the nodes in the tree. So now let's look at some new code. So just as in binary search tree, the first thing we implemented was the node. So for our AVL tree, we'll have an AVL tree node that inherits from the binary tree node. And we give it an additional attribute, right? Because for AVL tree, the important thing about each node is we have to know its height. So we add an additional attribute. I kind of just follow the normal practice of making it into a property and also make a setter for it. One of the maybe a little funky syntax, in case you haven't seen it before, is this single asterisk and double asterisk. This was talked about in 3B. If you haven't seen it before, here's a little link. You can read more about it if you want to, but basically all it means is whatever parameter that's passed into the dunder init method, it gets passed into as the way they are to the super dunder init, or in this case, the binary tree knows dunder init. And I think the most important parameter in these arguments is the data. Okay, so I have it here. I already typed it out here. Right. And oh well, and also obviously the reprieve method, and we'll use just the binary search trees reprieve, then the reprieve method that we just added with with the height of the I guess at the root node, at the node itself. Okay, and also the next thing is, yeah, we can now write the AVL tree. Now the AVL tree, as we said, it's only natural for it to inherit from the binary search tree. The first thing we need to do is remember the class attribute in the binary search tree node that we talked about. Now for the AVL tree, then obviously we want the AVL tree node, right? And that's all that it takes for now. It's we create the nodes in the AVL tree are AVL tree nodes. So very simple. The rest of the methods are all inherited from the binary search tree. So I have it here. I typed that already. Now the next thing is about just the test cases. So AVL tree is a binary tree. So whatever the binary search trees test cases, they should all work on an AVL tree. So we'll inherit that as well. And that's what we do here, the test code. So the AVL tree test case inherits from the binary search tree test cases. And again, as we kind of said a little earlier, is we want during setup, if you see during setup in the binary search tree test case, it's creating a binary search tree, obviously, but since we override it in our AVL tree test case with our own AVL tree, so in theory, we'll see that in a moment. In theory, then in the setup, it should create AVL trees rather than binary search trees. Okay, just want to say one thing. I mean, I'm still kind of exploring kind of inheriting test cases. There seems to be something good about it, something bad about it, but so far it seems to serve my needs, so that I'm going with that. So with just a few lines of code in the test as well as the implementation, we now claim that we have a bunch of test cases, and so let's make sure that is the case by running it. Now, so yeah, as you can see, the AVL tree test cases, they're all empty. There's nothing in there, but it does run all the tests that we wrote previously for the BST. Now, how do we know now, though, that all of these tests, they are testing an AVL tree, even though, again, the AVL tree for now is pretty much like a binary search tree? Well, so let's actually do um, print out the tree that was created during setup in the BST test cases. I remember this is the BST test, and inside there we actually created a tree with these data. So let's actually print it out and make sure we actually see the height in that tree, and there we go. So this is the tree. Remember that, yeah, the data we created was 23, whatever it was, yeah, 23, 8, 42, 4, and 1. And we also know now this tree is not a binary search tree because we have the height in there, and only the AVL trees node have height. Now, as you kind of see, the height, they're all 0. That's because, well, we haven't calculated the height yet, but they're there.